Picture this, the universe in its earliest moments, already bending the rules of time, allowing something or someone to traverse history before history even existed. What if time travel isn't just a sci-fi dream but a reality that happened at the very dawn of everything we know? Think about it. What if the universe's first act was a journey through time itself? Today, we're diving into 30 mind-bending theories that explore this very idea. From the Big Bang harboring secrets of cyclical time loops to black holes acting as natural time machines, these theories stretch the boundaries of science and imagination. Each one offers a unique perspective on how time travel might have been woven into the fabric of the universe from the start. So, buckle up, because by the end of this video, you'll not only question the nature of time but also wonder if the universe's first traveler is already out there waiting to be discovered. Let's begin this journey into the unknown. Now let's dive into our first theory. What if the Big Bang wasn't just a one-time event but part of an endless cycle? Imagine the universe as a loop where its beginning and end are not just connected but are essentially the same moment. This idea, known as the Big Bang as a time loop, suggests that the universe could be caught in an infinite cycle of birth, expansion, and collapse only to begin again. Picture this: every time the universe collapses, it triggers a new Big Bang, starting the process all over. This would mean that time itself could be cyclical, with no true beginning or end. Now, here's where it gets even more fascinating. If the universe is looping, could it also allow for time travel? Some physicists argue that under these conditions, the fabric of spacetime might fold in a way that makes moving through time possible. However, this theory isn't without its challenges. Many scientists question how such a cycle could sustain itself without losing energy or information over countless iterations. The debate continues, but one thing is clear: the idea of the Big Bang as a time loop pushes our understanding of time to its absolute limits. Could the universe's first act have been its last, and could that very loop hold the key to time travel? Now, shifting our focus to another intriguing possibility: wormholes. These theoretical tunnels through space-time have long captured the imagination of scientists and storytellers alike. But what if they aren't just science fiction? What if wormholes actually formed during the universe's creation? Think of the early universe as a chaotic, swirling soup of space-time. In such intense conditions, it's possible that tiny wormholes could have emerged, acting as shortcuts through the fabric of reality. Imagine these tunnels as bridges connecting distant points in space and time, potentially allowing for travel across both. If such wormholes existed, they could serve as natural time machines, offering a way to move backward or forward in time. But here's the catch: proving their existence is incredibly challenging. Wormholes are predicted by Einstein's theory of general relativity, but they're also incredibly unstable. They would require an enormous amount of exotic matter with negative energy to stay open, something we've yet to discover. Even if they did form during the universe's birth, their fleeting nature might make them nearly impossible to detect. Despite these hurdles, the idea of wormholes as time travel mechanisms continues to inspire researchers, pushing the boundaries of what we think is possible in the cosmos. Could these mysterious tunnels hold the key to the universe's first time travel event? The search for answers is far from over. Now, let's venture into the strange and fascinating world of quantum mechanics, a realm where the rules of reality seem to bend in ways that defy our everyday understanding. At the heart of this mystery lies quantum entanglement, a phenomenon so bizarre that even Einstein called it spooky action at a distance. Quantum entanglement occurs when two particles become so deeply linked that the state of one instantly influences the other, no matter how far apart they are. But here's where it gets even more intriguing. Some scientists theorize that this connection might not just bridge space but also time. Imagine two entangled particles existing at different points in the universe's timeline. If one particle's state changes, could it send a ripple backward or forward in time, effectively creating a temporal link? This idea suggests that entanglement could serve as a mechanism for the universe's first time travel event, where information or even matter could move instantaneously across time. Experiments have shown entanglement to be a real phenomenon, with particles maintaining their connection over vast distances. However, using this phenomenon for time travel remains purely theoretical. Current evidence doesn't show how entanglement could be harnessed to move objects or people through time, and the mechanisms for such a process are still unclear. Despite these limitations, the idea continues to spark curiosity, offering a glimpse into how the universe's fundamental building blocks might hold the key to unlocking the mysteries of time itself. Could quantum entanglement be the cosmic thread that ties the past, present, and future together? The exploration of this question is just beginning. Now, shifting our focus to an even grander scale, let's explore the concept of cosmic inflation and its potential role in time travel. In the earliest moments of the universe, just fractions of a second after the Big Bang, the cosmos underwent an unimaginably rapid expansion known as cosmic inflation. This period of exponential growth stretched spacetime itself, creating conditions that were anything but ordinary. As the universe ballooned in size, the fabric of spacetime could have been warped and twisted in ways that temporarily altered the flow of time. Imagine spacetime as a rubber sheet being pulled in all directions at once. Under such extreme conditions, temporary distortions or warps might have formed, creating pathways that allowed time to bend or even loop back on itself. These distortions could have acted as natural time machines, offering brief windows where particles, energy, or even physical objects could traverse time. While the idea is speculative, it's grounded in the physics of the early universe. Scientists theorize that such warps would have been fleeting, collapsing as inflation slowed and the universe settled into a more stable expansion. Yet the possibility remains that these early events could have left behind imprints, perhaps in the form of gravity waves or other cosmic signals, that we might one day detect. Cosmic inflation paints a picture of a universe where time itself was malleable, shaped by the intense forces of its birth. Could this rapid expansion have been the universe's first experiment with time travel? As we continue to study the remnants of this era, we may uncover clues that bring us closer to answering this profound question. Moving beyond our own universe, let's consider the mind-bending idea of the multiverse and how it might hold the key to the universe's first time travel event. The multiverse theory suggests that our universe is just one of countless others, each with its own unique physical laws and timelines. Imagine a vast cosmic tapestry where universes bubble up and expand, separated by unimaginable distances. But what if these universes aren't entirely isolated? What if a traveler from another universe found a way to bridge the gap and enter ours at the very moment of its creation? This traveler, whether an advanced being or a natural phenomenon, could have marked the first instance of time travel in our cosmic history. The multiverse theory opens up the possibility that time travel doesn't just happen within a single universe but across multiple realities. Picture this traveler arriving at the Big Bang, influencing the formation of space-time, and perhaps even leaving behind clues in the structure of our universe. While this idea remains speculative, it's supported by theories in physics that suggest interactions between universes could be possible under certain conditions. For instance, quantum fluctuations or cosmic strings might create pathways between universes, allowing for such crossings. Could this explain some of the mysteries we observe in our universe today? As we continue to explore the multiverse theory, we may uncover evidence that reshapes our understanding of time, space, and the very nature of existence itself. Now, let's turn our attention to one of the most fascinating objects in the cosmos, black holes. These mysterious regions of space-time, with their immense gravitational pull, have long captured our imagination. But could they also serve as natural time machines? The idea hinges on the extreme conditions near a black hole, where gravity is so intense that it warps space-time itself. According to Einstein's theory of general relativity, time slows down near a massive object like a black hole. This phenomenon, known as gravitational time dilation, suggests that if you were to approach a black hole, time for you would pass more slowly compared to someone far away. Now, imagine a journey where you orbit a black hole for a period and then return. You might find that years or even centuries have passed for the rest of the universe while only a short time has elapsed for you. In essence, you've traveled into the future, but could black holes also allow travel into the past? Some theories propose that certain types of black holes, like rotating ones known as Kerr black holes, might contain what's called a closed time-like curve. This hypothetical pathway could theoretically allow you to loop back to an earlier point in time, effectively enabling backward time travel. In the early universe, black holes were among the first structures to form, and their immense gravity could have created temporary distortions in spacetime. These distortions might have opened brief windows for time travel, marking some of the earliest instances in cosmic history. While these ideas remain speculative, they challenge our understanding of time and space, offering a tantalizing glimpse into the possibilities hidden within the universe's darkest corners. As we continue to explore black holes, we may uncover clues that transform science fiction into science fact. Now, let's explore one of the most famous puzzles in the realm of time travel, the grandfather paradox. Imagine a scenario where a time traveler goes back in time and prevents their grandfather from meeting their grandmother. If this happens, the traveler would never be born, which means they couldn't have traveled back in time in the first place. This paradox has long been a stumbling block for time travel theories, but what if the early universe held the key to resolving it? In the first moments after the Big Bang, the laws of physics as we know them may have been vastly different. Some scientists speculate that the extreme conditions of the infant universe could have allowed for alternate timelines or parallel realities to coexist. This means that if a time traveler were to alter the past, they might not erase their own history but instead create a new, branching timeline. In this way, the original timeline remains intact, avoiding the paradox altogether. Another intriguing idea is that the universe's early state of quantum uncertainty could have absorbed such changes without collapsing into a contradiction. Particles in the quantum realm exist in multiple states until observed, so perhaps actions in the past could remain unresolved until they no longer conflict with the present. While these theories are speculative, they offer fascinating possibilities for how time travel could operate in the universe's infancy without unraveling the fabric of reality. As we delve deeper into the mysteries of the early cosmos, we may uncover clues that not only resolve the grandfather paradox but also reshape our understanding of time itself. Next, we'll examine how the universe's first temporal structures, known as time crystals, might have played a role in enabling these early time travel events. Now, let's turn our attention to one of the most intriguing concepts in modern physics, time crystals. Unlike ordinary crystals, which have repeating patterns in space, time crystals are structures that repeat their patterns over time, creating a kind of perpetual motion without energy loss. First proposed in 2012, these hypothetical structures have sparked excitement among scientists for their potential to revolutionize our understanding of time itself. In the early universe, conditions were so extreme that they might have allowed time crystals to form. These temporal structures could have acted as natural clocks, ticking away in the chaotic aftermath of the Big Bang. But here's where it gets really interesting. Some researchers believe time crystals could have served as the first pathways for time travel. By breaking the symmetry of time, they might have created stable loops or cycles, allowing particles or even information to traverse backward or forward in time. Imagine a universe where the very fabric of time was shaped by these repeating patterns, opening up possibilities for travel between moments that would otherwise be out of reach. While the existence of time crystals is still theoretical, Experiments in recent years have brought us closer to understanding how they might work. If they did exist in the early universe, they could have laid the groundwork for the first instances of time travel, offering a glimpse into how the cosmos might have bent its own rules. As we continue to explore this fascinating idea, we're reminded that the universe's earliest moments may have been far stranger and more connected to time travel than we ever imagined. Next, we'll investigate how dark matter, the invisible force shaping our cosmos, might have influenced these early temporal phenomena. Now, let's shift our focus to one of the universe's greatest mysteries, dark matter. This invisible substance makes up more than 80% of the universe's total mass, yet it doesn't interact with light, making it nearly impossible to observe directly. Despite its elusive nature, dark matter's gravitational influence is immense, shaping galaxies and clusters on a cosmic scale. But could it have also played a role in the universe's first instances of time travel? Some scientists believe that dark matter's gravitational effects might have created subtle distortions in spacetime, altering the flow of time itself. In the early universe, where everything was densely packed and highly energetic, these distortions could have been significant enough to open up pathways for particles, or even larger structures, to move through time. Imagine dark matter as an unseen sculptor, bending the fabric of spacetime in ways that allowed time travel to occur naturally. While this idea remains speculative, it's a compelling thought that connects one of the universe's biggest mysteries to the tantalizing possibility of traversing time. As we continue to uncover the secrets of dark matter, we may find that its role in the cosmos goes far beyond what we currently understand, potentially unlocking new insights into the nature of time itself. Next, we'll explore how the holographic principle suggests that the universe could be a projection, and how this might relate to early time travel events. Shifting gears, let's explore a mind-bending idea that could reshape how we think about the universe and time travel, the holographic principle. This theory suggests that everything we see in our three-dimensional universe might actually be a projection from a two-dimensional surface, like a cosmic hologram. Just as a hologram can encode three-dimensional information on a flat surface, the universe might store all its data on a two-dimensional boundary. If this is true, it could mean that time and space are not fundamental but rather emerge from this deeper layer of information. Now, here's where it gets even more fascinating. If the universe is essentially a hologram, manipulating this underlying information could allow for extraordinary possibilities, including time travel. Imagine accessing the universe's source code and altering it to move through time, almost like rewinding or fast-forwarding a video. While this concept is still in the realm of theory, it opens up a new way to think about how time travel might work, not by bending spacetime itself, but by changing the information that constructs it. The holographic principle challenges our understanding of reality and offers a unique perspective on how the universe's first time travel events could have occurred. As we continue to push the boundaries of physics, this idea might just hold the key to unlocking one of the universe's greatest mysteries. Next, we'll delve into the concept of quantum tunneling and its potential role in the earliest moments of time travel. Now, let's venture into the strange and unpredictable world of quantum mechanics, where particles defy the rules we're used to in our everyday lives. This brings us to quantum tunneling, a phenomenon that might just hold the key to understanding the universe's first time travel events. Quantum tunneling occurs when particles pass through barriers that, according to classical physics, should be impossible to cross. Think of it like a ball rolling up a hill and somehow making it to the other side without having enough energy to get over the top. In the quantum realm, particles can tunnel through these barriers, appearing on the other side as if by magic. Now, imagine this concept applied to time itself. During the universe's earliest moments, the fabric of spacetime was incredibly unstable, filled with fluctuations and barriers that particles had to navigate. If quantum tunneling allowed particles to bypass these barriers, it's possible that some of them could have traveled through time in the process. This wouldn't be time travel as we typically imagine it, like hopping into a machine and moving to a different era. Instead, it would be a natural, quantum-level phenomenon where particles briefly slipped through time, perhaps even influencing the unfolding of the universe in ways we're only beginning to understand. While this idea is still speculative, it's supported by the principles of quantum mechanics, which show that particles don't always follow the predictable paths we expect. The universe's first moments were a playground of quantum possibilities, and tunneling could have been one of the mechanisms that allowed time travel to occur. As we continue to study these early moments, quantum tunneling offers a fascinating lens through which to explore how time might have been bent, twisted, or even bypassed altogether. Next, we'll turn our attention to neutrinos and their potential role in the universe's earliest time travel events. Shifting our focus to the enigmatic world of subatomic particles, let's explore the role of neutrinos in the universe's earliest moments. Neutrinos are fascinating in their own right: tiny, nearly massless particles that zip through space at incredible speeds, often without interacting with matter at all. Their ghostly nature makes them incredibly hard to detect, but it also opens up intriguing possibilities when it comes to time travel. In the chaotic environment of the early universe, neutrinos could have played a unique role in the fabric of spacetime. Because they interact so weakly with other particles, they might have slipped through spacetime in ways that heavier particles couldn't. Picture this: as the universe expanded rapidly during cosmic inflation, spacetime itself was stretching and warping. Neutrinos, with their minimal mass and near light-speed movement, could have been carried along these warps, potentially creating pathways through time. This idea gets even more interesting when we consider how neutrinos might have influenced the universe's development. If they traveled through space-time in unconventional ways, they could have carried information or energy from one point in time to another, subtly shaping the conditions of the early universe. While this isn't time travel in the traditional sense, it suggests that neutrinos might have been key players in the universe's first temporal experiments. Of course, this theory is still in its infancy, and much remains to be discovered about neutrinos and their interactions with spacetime. But as we continue to study these elusive particles, they offer a compelling perspective on how time itself might have been manipulated in the universe's formative moments. Next, we'll examine the infinite universe's hypothesis and its implications for time travel. Now, let's venture into the mind-bending concept of the infinite universe's hypothesis. Imagine for a moment that our universe is just one of countless others, each with its own unique set of physical laws and timelines. The idea of a multiverse suggests that there could be an infinite number of parallel realities, each existing simultaneously but independently of one another. This raises a fascinating question. If there are infinite universes, could time travel have already occurred in some of them? And if so, what would that mean for our own universe's history? The infinite universe's hypothesis opens up a realm of possibilities when it comes to time travel. In some universes, the laws of physics might allow for straightforward time travel, where individuals or objects can move freely between past, present, and future. In others, time travel might be a rare, accidental event, perhaps triggered by cosmic anomalies or advanced civilizations experimenting with the fabric of spacetime. The sheer diversity of these universes means that time travel could take on countless forms, each with its own unique set of rules and consequences. What's particularly intriguing is how these other universes might intersect with our own. If time travel has occurred in other realities, could there be indirect effects or echoes that ripple into our universe? For instance, a time traveler from another universe might leave behind subtle traces or distortions in spacetime, detectable only through sophisticated scientific instruments. Alternatively, the act of time travel in one universe might influence the development of another, creating a complex web of cause and effect across the multiverse. This theory also challenges our understanding of history and causality. If time travel is possible in other universes, does that mean the events in our own universe are fixed, or could they be influenced by actions in parallel realities? The infinite universes hypothesis doesn't just expand our horizons, it forces us to rethink the very nature of time, space, and our place within the cosmos. As we continue to explore this theory, it invites us to consider not just the possibilities of time travel, but the interconnectedness of all things in an infinite multiverse. Next, we'll look into the idea of the universe's first temporal anomalies and how they might have allowed for brief instances of time travel. Now, shifting our focus to the earliest moments of the universe, we encounter the intriguing possibility of the first temporal anomalies. Picture this: in the chaotic aftermath of the Big Bang, space-time itself was still taking shape, unstable and prone to irregularities. During this period, it's theorized that brief distortions in time, temporal anomalies, may have emerged, creating fleeting opportunities for time travel. These anomalies could have arisen from the intense conditions of the early universe, where extreme temperatures and pressures warped the fabric of space-time in ways we can scarcely imagine. Think of it as a boiling pot of water where bubbles of steam rise and pop rapidly. In a similar fashion, the universe's infancy might have produced bubbles of distorted time, allowing particles, energy, or even information to traverse moments that would otherwise be impossible to bridge. What's fascinating about these anomalies is that they could have happened spontaneously, without any external force or technology. Unlike the deliberate manipulation of time we often imagine in science fiction, these early instances of time travel would have been entirely natural, driven by the universe's raw, primordial energy. This suggests that time travel might not be as far-fetched as it seems. It could have been an inherent feature of the cosmos from the very beginning. Of course, detecting evidence of these temporal anomalies is no easy task. The universe has since cooled and expanded, smoothing out the wrinkles in spacetime that may have once existed. However, some scientists hypothesize that remnants of these anomalies could still be hidden within the cosmic microwave background, the faint afterglow of the Big Bang. If we could decode its subtle patterns, we might uncover clues that point to these early disruptions in time. This theory also raises questions about causality in the early universe. If temporal anomalies allowed for brief time travel, could they have influenced the formation of galaxies, stars, or even the fundamental laws of physics? It's a thought that challenges our understanding of how the universe evolved and invites us to reconsider the role of time in shaping reality. As we move forward, let's explore how dark energy might have further influenced space-time, creating even more opportunities for time travel. Now, turning our attention to the vast and mysterious force known as dark energy, we uncover yet another layer of possibility in the quest for the universe's first time travel. Dark energy, which makes up roughly 68% of the universe, is the driving force behind its accelerated expansion. But what if this enigmatic energy also played a role in shaping the very fabric of spacetime to allow for time travel? Imagine dark energy as a kind of cosmic accelerator, stretching spacetime faster and faster over time. This rapid expansion could have created unique conditions where the usual rules of time and space no longer apply. In the early universe, when dark energy's effects were just beginning to take hold, it's possible that spacetime was stretched thin enough to allow for temporary distortions or wrinkles. These distortions might have opened up pathways for time travel, even if only for the briefest moments. One intriguing idea is that dark energy could have acted as a kind of cosmic time machine, pulling spacetime apart so violently that it created regions where time moved differently. For example, in areas where dark energy was particularly strong, time might have slowed down or speeded up relative to the rest of the universe. This could have created opportunities for particles, energy, or even information to travel through time, either forward or backward. But how could dark energy have achieved this? Think of spacetime as a rubber sheet. Normally, this sheet is smooth and uniform, but if you pull it rapidly in all directions, tiny tears or ripples can form. In the same way, dark energy's relentless expansion might have caused spacetime to ripple or warp, creating temporary anomalies that allowed for time travel. These anomalies could have been fleeting, lasting only fractions of a second, but in the early universe, even such brief moments could have had profound effects. The challenge, of course, is detecting evidence of these dark energy-induced time travel opportunities. The universe has been expanding for billions of years, and any traces of these early distortions have likely been smoothed out. However, some scientists believe that dark energy's influence on large-scale structures, like galaxies and galaxy clusters, might hold clues. By studying how these structures have evolved over time, we might uncover subtle hints of dark energy's role in shaping spacetime in ways that allowed for time travel. This theory also raises fascinating questions about the nature of time itself. If dark energy could stretch spacetime to the point of enabling time travel, what does that say about the relationship between time and the universe's expansion? Could time travel be an inherent feature of a universe dominated by dark energy? As we continue to explore the mysteries of the cosmos, the role of dark energy in time travel remains an exciting and open question. Next, we'll delve into the possibility of a universe's first time traveler, and whether an advanced civilization from the future might have left its mark on our past. Turning our gaze to an even more speculative notion, let's consider the idea that the universe's first time traveler might not have been a natural phenomenon but an advanced being from the future. Picture this: what if a civilization far more advanced than ours, perhaps millions or even billions of years ahead, had mastered the art of time travel? Could they have journeyed back to the very dawn of the universe, leaving behind traces of their presence? This theory opens up a realm of possibilities. If such a civilization existed, their motivations for traveling to the universe's infancy could vary widely. Perhaps they sought to study the origins of everything, to witness the Big Bang firsthand, or even to influence the universe's development in ways that would shape their own future. On the other hand, their journey might have been accidental, a consequence of experiments with time travel technology gone awry. One of the most intriguing aspects of this idea is the question of evidence. If an advanced civilization did visit the early universe, what traces might they have left behind? Some scientists speculate that subtle anomalies in the cosmic microwave background, radiation, or irregularities in the distribution of galaxies could hint at an artificial influence. Others suggest that certain unexplained phenomena, like the mysterious fast radio bursts detected by astronomers, might be signals or artifacts left by time travelers. Of course, the challenge lies in distinguishing between natural cosmic events and potential signs of intelligent interference. The universe is vast and filled with phenomena we are only beginning to understand. Still, the possibility that an advanced civilization could have altered or observed the universe's earliest moments is both thrilling and thought-provoking. This theory also raises profound questions about the nature of time and causality. If a future civilization could travel back to the universe's beginning, does that mean the timeline is fixed, or could their actions have created alternate realities? Could their presence have set off a chain of events that ultimately led to their own existence? These questions push the boundaries of our understanding and invite us to rethink our place in the cosmos. As we ponder the idea of the universe's first time traveler, it's worth considering what this means for humanity. If such a civilization exists, could we one day follow in their footsteps? Or are we, perhaps, the ones who will eventually make that journey? The answers remain elusive, but the questions themselves remind us of the endless mysteries waiting to be uncovered. Next, we'll explore the role of superstrings in time travel and how these theoretical constructs might have shaped the universe's earliest moments. shifting our focus to a more fundamental level of the universe, let's delve into the fascinating concept of superstring theory and its potential connection to time travel. According to this theory, the universe isn't made up of point-like particles but of tiny, vibrating strings. These strings, each one-dimensional and unimaginably small, vibrate at different frequencies, giving rise to all the particles and forces we observe in the cosmos. Now imagine these strings not just as the building blocks of matter, but as potential keys to unlocking time travel. If these vibrations could be controlled or manipulated, it's possible they could create pathways through spacetime, effectively allowing for travel to different points in time. In the early universe, when conditions were far more extreme and energies unimaginably high, these strings might have interacted in ways that opened temporary portals or shortcuts through time. One of the most intriguing aspects of superstring theory is the idea that these strings could exist in higher dimensions, up to 10 or 11 according to some models. These extra dimensions, hidden from our everyday perception, might hold the secret to bending spacetime in ways that make time travel possible. For instance, a string vibrating in a higher dimension could theoretically bypass the linear flow of time we experience, creating a bridge between past, present, and future. But how does this apply to the universe's first moments? During the Big Bang, the extreme density and energy of the early cosmos could have caused these strings to vibrate in ways that created temporary temporal loops or wormholes. These structures might have allowed particles or even entire systems to traverse time, marking the first instances of time travel in the universe. The challenge, of course, is that superstring theory remains largely theoretical. While it offers a compelling framework for understanding the universe's fundamental nature, we lack the technology or evidence to test its predictions directly. However, the idea that the earliest moments of the cosmos were shaped by the vibrations of tiny strings opens up a universe of possibilities, one where time itself may have been far more malleable than we ever imagined. As we continue to explore the mysteries of the early universe, superstring theory reminds us that the fabric of reality may be far stranger and more interconnected than we've ever realized. Next, we'll examine how the cosmic microwave background, the faint afterglow of the Big Bang, might hold clues to the universe's first time travel events. Turning our attention to the echoes of the universe's birth, the cosmic microwave background offers a fascinating window into the past. This faint afterglow, often referred to as the first light of the universe, is the residual heat from the Big Bang itself. Stretching across the entire cosmos, it's a snapshot of the universe when it was just 380,000 years old. But could this ancient radiation also hold clues to the universe's first time travel events? The cosmic microwave background is like a cosmic fingerprint, carrying imprints of the conditions and events that shaped the early universe. Scientists have long studied its tiny fluctuations, which reveal the seeds of galaxies and large-scale structures we see today. But some researchers have speculated that these fluctuations might also hint at something even more extraordinary: temporal anomalies. Imagine if, in the chaotic moments following the Big Bang, brief instances of time travel occurred. Particles or energy moving backward in time could have left subtle imprints in the cosmic microwave background, detectable as irregularities or patterns that don't fit the standard model of cosmology. For example, unusual temperature variations or unexpected polarization patterns could be the telltale signs of early time travel. One intriguing possibility is that temporal loops or closed time-like curves existed in the universe's infancy, allowing particles to interact with their past or future selves. These interactions could have influenced the distribution of matter and energy, leaving behind faint traces in the cosmic microwave background. While these traces would be incredibly subtle, advancements in observational technology might one day make them detectable. The search for such evidence is still in its early stages, but the idea is captivating. If we could decode these ancient signals, it might not only confirm the existence of time travel in the universe's first moments, but also deepen our understanding of spacetime itself. As we peer into the cosmic microwave background, we're not just looking at the universe's past, we're potentially uncovering the first hints of its temporal history. Next, we'll explore how gravity waves, the ripples in spacetime caused by massive cosmic events, might have played a role in the universe's earliest time travel phenomena. Shifting our focus to the dynamic fabric of spacetime, let's consider how gravity waves might have played a role in the universe's earliest time travel events. These ripples, caused by massive cosmic events like colliding black holes or neutron stars, are more than just echoes of violence in the cosmos. They could be key to understanding the potential for time travel in the universe's infancy. Picture the universe in its first moments, a seething cauldron of energy and matter. As massive objects formed and interacted, they would have generated powerful gravity waves, distorting the very fabric of spacetime. But could these distortions have created temporary pathways for time travel? Some scientists theorize that under the extreme conditions of the early universe, gravity waves might have been strong enough to bend spacetime into loops or curves, allowing particles or energy to traverse time itself. One possibility is that gravity waves could have interacted with other phenomena, like wormholes or quantum fluctuations, to create fleeting opportunities for time travel. Imagine a gravity wave passing through a nascent wormhole, stabilizing it just long enough for something or someone to move through it. Alternatively, gravity waves might have amplified the effects of quantum mechanics, enabling particles to tunnel through time in ways that would be impossible under normal conditions. The challenge, of course, is detecting evidence of these events. Gravity waves from the early universe would be incredibly faint by the time they reach us, masked by the noise of more recent cosmic events. Yet, advancements in technology like the Laser Interferometer Gravitational Wave Observatory, or LIGO, are bringing us closer to detecting these ancient ripples. If we could observe gravity waves from the universe's first moments, we might uncover clues about how they interacted with spacetime, potentially revealing the first instances of time travel. The idea that gravity waves could have enabled time travel in the early universe is both thrilling and speculative. It challenges us to rethink our understanding of spacetime and the forces that shape the cosmos. As we continue to explore this theory, we're reminded that the universe's mysteries are as vast as they are profound. Up next, we'll delve into the concept of closed time-like curves and how they might have existed in the universe's earliest moments. Now, let's turn our attention to a fascinating idea that could redefine how we think about time travel: closed time-like curves. These hypothetical pathways through spacetime are theorized to allow an object or even a person to travel back in time without creating the kind of paradoxes we often associate with such journeys. Imagine a loop in time where the end connects seamlessly to the beginning, creating a self-contained cycle. In the universe's earliest moments, conditions were so extreme that such curves might have naturally formed, offering a potential mechanism for the first instances of time travel. To understand closed time-like curves, think of spacetime as a fabric that can be bent or twisted. Under certain conditions, this fabric might curve back on itself, creating a loop where time moves in a circle rather than a straight line. In this scenario, an object following the curve would return to its own past, repeating the same events over and over. While this might sound like science fiction, it's a concept that emerges from the equations of general relativity, the same framework that describes gravity and the large-scale structure of the universe. In the early universe, the rapid expansion and intense energy might have warped spacetime in ways that allowed closed time-like curves to form. Picture a universe still in its fiery infancy, where spacetime was more flexible, almost like a malleable clay. Under these conditions, it's possible that loops in time could have appeared spontaneously, creating opportunities for particles, or even more complex entities, to travel backward in time without disrupting the flow of causality. One of the most intriguing aspects of closed time-like curves is how they could resolve the grandfather paradox, the classic problem of time travel where changing the past creates a logical inconsistency. In this model, events within the curve are self-consistent. Nothing can happen that would alter the past in a way that contradicts itself. It's as if the universe ensures that any journey through time remains coherent, preserving the timeline's integrity. Detecting evidence of closed time-like curves in the early universe is, of course, a monumental challenge. These structures, if they existed, would have been fleeting, disappearing as the universe cooled and stabilized. Yet the possibility remains tantalizing. Advanced theoretical models and future observations of cosmic phenomena might one day offer clues about whether these temporal loops played a role in the universe's first moments. The idea of closed time-like curves opens up a world of possibilities, challenging us to rethink the nature of time itself. As we continue to explore this theory, we're reminded that the early universe was a place of incredible potential, where the rules of physics as we know them were stretched to their limits. Next, we'll examine the role of antimatter in time travel and how it might have interacted with spacetime during the universe's formation. Now, let's dive into another captivating theory that takes us deeper into the mysteries of the early universe, the role of antimatter in time travel. Antimatter, often described as the mirror image of ordinary matter, has long fascinated scientists for its potential to unlock secrets about the cosmos. But what if it also held the key to the universe's first instances of time travel? At the heart of this theory lies the idea that antimatter, with its unique properties, could have interacted with spacetime in ways that matter alone could not. In the early universe, moments after the Big Bang, matter and antimatter were created in nearly equal amounts. Their interactions were explosive, releasing immense energy and shaping the fabric of spacetime itself. Could these interactions have created temporary distortions or anomalies that allowed for time travel? Antimatter is known for its ability to annihilate matter upon contact, producing bursts of energy. This process might have had profound effects on the early universe's structure. Imagine a universe so hot and dense that every collision between matter and antimatter warped spacetime, creating ripples or even temporary pathways through time. These pathways, though fleeting, could have provided the first opportunities for particles, or perhaps even more complex entities, to traverse time. One particularly intriguing possibility is that antimatter, with its opposite charge and behavior, might have interacted with spacetime in reverse. Think of it like rewinding a tape. While matter moves forward in time, antimatter could theoretically move backward. If this were the case, antimatter might have played a crucial role in creating closed loops or bridges in spacetime, enabling the first instances of time travel. Of course, this theory is highly speculative, and detecting evidence of antimatter's role in time travel is a daunting challenge. Antimatter is incredibly rare in the universe today, and reconstructing its behavior in the early universe requires advanced theoretical models and cutting-edge experiments. Yet, scientists continue to explore this possibility, driven by the tantalizing idea that antimatter could hold the key to understanding time itself. The role of antimatter in time travel invites us to rethink our understanding of the universe's earliest moments. It's a reminder that the cosmos was once a place of unimaginable energy and potential, where the rules of physics as we know them were still being written. Next, we'll explore another fascinating idea: how the universe's first temporal paradoxes might have shaped the possibilities of time travel. Now, let's shift our focus to a theory that challenges our very understanding of time: the possibility that the universe's earliest moments were shaped by temporal paradoxes. A temporal paradox occurs when an event in time contradicts itself, creating a loop or inconsistency that defies logic. But what if such paradoxes weren't just theoretical? What if they were integral to the universe's formation and the first instances of time travel? In the chaotic aftermath of the Big Bang, the laws of physics as we know them may not have fully applied. imagine a universe so young and unstable that even the concept of cause and effect was fluid. In this environment, temporal paradoxes could have emerged naturally, allowing events to occur out of sequence or even contradict one another. These paradoxes might have opened up temporary windows where time travel became not just possible but inevitable. One of the most well-known paradoxes is the grandfather paradox, where a time traveler goes back in time and accidentally prevents their own existence. But in the early universe, such paradoxes might not have caused the collapse of reality. Instead, they could have been resolved through mechanisms we don't yet understand. For instance, the universe's extreme energy and density might have allowed multiple timelines or outcomes to coexist, sidestepping the paradox entirely. Another possibility is that temporal paradoxes in the early universe weren't anomalies, they were features. Think of them as knots in the fabric of space-time, creating connections between different moments in time. These knots could have acted as natural time travel pathways, enabling particles or energy to move between points in time without breaking the universe's fundamental laws. While this idea is speculative, it raises fascinating questions about the nature of time itself. Could paradoxes have been the universe's way of experimenting with time travel? And if so, might we find evidence of these early paradoxes hidden in the cosmic microwave background or other remnants of the Big Bang? Scientists are still exploring these ideas, driven by the tantalizing possibility that the universe's first moments were far more complex and interconnected than we ever imagined. The notion of temporal paradoxes in the early universe invites us to consider that time might not always follow the linear path we experience today. It's a reminder that the cosmos was once a place of boundless creativity, where even the rules of logic were open to interpretation. Next, we'll delve into another intriguing concept, the role of exotic matter in shaping the universe's first time travel mechanisms. Now, let's turn our attention to a theory that introduces a truly mind-bending concept, the role of exotic matter in the universe's first time travel. Exotic matter, as the name suggests, isn't your typical building block of the cosmos. Unlike the matter we're familiar with, exotic matter possesses something called negative energy density, a property that defies our everyday understanding of physics. But how could this strange substance have played a part in time travel during the universe's earliest moments? One of the key ideas here involves wormholes, those theoretical tunnels through space-time that could connect distant points in time and space. While wormholes are fascinating in theory, they have a major problem. They're incredibly unstable. According to calculations, a wormhole would collapse almost instantly under the weight of its own gravity. But this is where exotic matter comes in. With its negative energy density, exotic matter could theoretically counteract the forces that cause wormholes to collapse, stabilizing them long enough to serve as time travel pathways. In the early universe, conditions were extreme enough that exotic matter might have naturally existed, even if only for a fleeting moment. The immense energy and density of the cosmos could have created the perfect environment for this unusual substance to form and interact with space-time. Imagine exotic matter acting as a sort of cosmic glue, holding open wormholes or other time travel mechanisms just long enough for particles, or perhaps even more complex structures, to traverse them. But what does this mean for the first instances of time travel? If exotic matter stabilized wormholes in the early universe, it's possible that these tunnels weren't just theoretical, they might have been functional. Particles, energy, or even information could have traveled through these wormholes, creating connections between different points in time. This would mean that the universe's first time travel events weren't random occurrences, but the result of a complex interplay between exotic matter and space-time itself. While this idea remains speculative, it's a testament to the creativity of theoretical physics. Exotic matter offers a tantalizing solution to one of the biggest challenges in time travel research: how to make the impossible possible. As scientists continue to explore this concept, They're not just studying the early universe, they're uncovering clues about the very nature of reality. Next, we'll explore another fascinating possibility, the universe's first natural time machine. Now, let's shift our focus to a theory that feels almost like science fiction, but is grounded in the intriguing possibilities of physics. The idea that the early universe might have hosted its very first natural time machine. Imagine a cosmic mechanism formed by the extreme conditions of the universe's infancy, capable of bending the rules of time itself. This concept takes us beyond wormholes and exotic matter, suggesting that time travel could have been a built-in feature of the cosmos from the very beginning. The early universe was a place of unimaginable energy and density, where the laws of physics operated in ways we're still struggling to understand. In this chaotic environment, it's possible that natural phenomena like black holes, quantum fluctuations, or even the fabric of spacetime itself could have created temporary time loops or pathways. These structures might have acted as natural time machines, allowing for the first instances of time travel without the need for advanced technology or exotic matter. One intriguing possibility is that primordial black holes formed in the universe's earliest moments could have played a role. These ancient black holes, smaller yet denser than their modern counterparts, might have generated gravitational fields powerful enough to warp spacetime into closed time-like curves, paths that loop back on themselves in time. If particles or energy entered these curves, they could have traveled backward or forward in time, marking the universe's first forays into temporal manipulation. Another angle considers quantum mechanics, which suggests that at the smallest scales, particles can behave in ways that defy classical physics. In the early universe, quantum effects were dominant, and it's possible that these tiny, unpredictable behaviors could have created temporary time travel opportunities. For instance, quantum tunneling, where particles bypass barriers they shouldn't be able to cross, might have allowed particles to jump through time, effectively creating a rudimentary form of time travel. What makes this theory so compelling is its simplicity. Unlike wormholes or exotic matter, which require highly specific and rare conditions, a natural time machine could have been a byproduct of the universe's birth, an accidental yet revolutionary feature of the cosmos. If true, this would mean that time travel wasn't just possible but perhaps even inevitable in the universe's earliest moments. While this idea remains speculative, it challenges us to rethink our assumptions about time and its origins. It suggests that the universe's first time traveler might not have been a person or even a particle. It could have been time itself, bending and looping in ways we're only beginning to understand. Next, we'll explore another fascinating aspect of the universe's early days, the role of plasma in enabling time travel. Now, let's dive into another fascinating layer of the early universe's story, the role of plasma in shaping the possibilities of time travel. Picture this: the universe, just moments after the Big Bang, was a seething ocean of plasma, a superheated state of matter where atoms hadn't even formed yet. It was a chaotic, energetic soup of charged particles, and within this chaos something extraordinary might have happened. Plasma, in its simplest form, is a collection of free electrons and ions, particles that carry electric charge. In the early universe, this plasma was everywhere, and it interacted with the fabric of space-time in ways we're only beginning to understand. The intense energy and movement of these charged particles could have created ripples in space-time, temporary distortions that might have opened windows for time travel. One idea is that these plasma-driven distortions could have formed what physicists call temporal vortices, regions where time flows differently from the rest of space. In these vortices, time might have slowed down, sped up, or even looped back on itself, creating opportunities for objects or particles to move through time in ways that would otherwise be impossible. Another angle considers the electromagnetic fields generated by plasma. In the early universe, these fields were incredibly strong and turbulent, and they might have twisted space-time in ways that created shortcuts or pathways through time. Think of it like a river with whirlpools. The plasma's electromagnetic fields could have spun spacetime into structures that allowed for brief moments of time travel. What's particularly intriguing about this theory is how grounded it is in the physics of the early universe. Plasma wasn't a rare or exotic phenomenon. It was the dominant state of matter for hundreds of thousands of years after the Big Bang. If plasma did create opportunities for time travel, it would mean that the universe's first forays into temporal manipulation were not just possible but perhaps even common. Of course, this idea is still speculative, but it opens up a new way of thinking about the early universe. It suggests that time travel might not require advanced technology or exotic matter. It could have been a natural consequence of the universe's fiery beginnings. As we continue to explore the mysteries of the cosmos, the role of plasma reminds us that even the most familiar states of matter can hold extraordinary secrets. Next, we'll turn our attention to another intriguing possibility: the first temporal loops in the universe's infancy and how they might have enabled time travel. Stepping into a new layer of cosmic mystery, let's explore the concept of temporal loops and how they might have played a role in the universe's earliest moments. Imagine a scenario where time doesn't just move forward in a straight line, but instead folds back on itself, creating a loop where events repeat endlessly. This idea, known as a temporal loop, could have been a natural feature of the universe's infancy, offering a unique pathway for time travel. In the first moments after the Big Bang, the universe was a place of extreme energy and instability. Under such conditions, the fabric of spacetime might have been twisted and warped in ways that allowed for the formation of these temporal loops. Picture a piece of fabric crumpled into a ball. Spacetime could have folded in on itself, creating loops where time circles back to an earlier point. These loops could have allowed particles or even larger structures to travel back in time within the loop, effectively revisiting the same moment over and over. This wouldn't just be a one-way trip, it would be a continuous cycle where the same events repeat in an endless sequence. For example, a particle caught in a temporal loop might experience the same moment multiple times, becoming a kind of cosmic echo of itself. One of the most fascinating aspects of this theory is how it aligns with certain ideas in modern physics. For instance, the concept of closed time-like curves where an object can return to its own past shares similarities with temporal loops. In the early universe, these loops might have been naturally occurring, created by the intense gravitational and quantum forces at play. But how could such loops enable time travel? The answer lies in the nature of the loops themselves. If a loop exists, anything caught within it would be able to move backward in time to an earlier point in the loop. This means that, in theory, an object or even information could travel back in time within the loop without disrupting the overall flow of time in the universe. What's intriguing is that these loops wouldn't require any advanced technology or exotic matter. They could have been a natural consequence of the universe's chaotic beginnings. If temporal loops did exist, they would represent one of the earliest and most fundamental forms of time travel, woven into the fabric of the cosmos itself. As we ponder this idea, it's worth considering how it might connect to other theories about the universe's first moments. Temporal loops could have interacted with phenomena like plasma or quantum fluctuations, creating a dynamic and interconnected web of possibilities for time travel. Next, we'll turn our attention to another intriguing piece of this cosmic puzzle: the role of primordial black holes in the universe's potential for time travel. Now, let's delve into the fascinating role of primordial black holes in the universe's potential for time travel. These black holes, formed in the earliest moments after the Big Bang, might hold the key to understanding some of the first instances of time travel. Unlike the black holes we're familiar with today, primordial black holes were incredibly small yet extraordinarily dense, and they could have existed in vast numbers across the young universe. Primordial black holes are thought to have formed from the intense fluctuations in density during the universe's rapid expansion. These fluctuations created pockets of matter so dense that they collapsed under their own gravity, giving rise to these miniature black holes. Because of their size and density, they could have exerted a significant influence on the surrounding spacetime, potentially warping it in ways that allowed for time travel. Imagine a primordial black hole as a tiny but powerful knot in the fabric of spacetime. Its immense gravitational pull could have created what's known as a closed time-like curve, a path through spacetime that loops back on itself. If an object or particle were to enter such a curve, it could theoretically travel back in time, revisiting an earlier moment in its own history. What makes primordial black holes especially intriguing is their age. Since they formed so early in the universe's history, they might have been among the first natural structures capable of enabling time travel. This means that, long before any advanced civilizations or technologies existed, the universe could have already been experimenting with time travel through these ancient black holes. Another compelling aspect of this theory is the potential for these black holes to interact with other phenomena in the early universe. For instance, they could have influenced the behavior of plasma, quantum fluctuations, or even dark matter, creating a complex interplay that further enhanced their time-bending capabilities. But how could we ever detect these primordial black holes, assuming they still exist today? One possibility is that they could leave behind subtle clues in the cosmic microwave background, the faint afterglow of the Big Bang. If primordial black holes played a role in shaping the early universe, their fingerprints might still be visible in this ancient light. As we explore the idea of primordial black holes as natural time machines, it's worth considering how they might connect to other theories about the universe's first moments. Could they have interacted with temporal loops, wormholes, or even the multiverse? The possibilities are as vast as the cosmos itself. Next, we'll shift our focus to another intriguing concept, the universe's first temporal displacement and how it might have paved the way for time travel. Moving forward, let's explore the concept of temporal displacement and its potential role in the universe's earliest moments. Temporal displacement refers to the idea that objects or particles could have moved through time, not just space, during the universe's formation. This idea challenges our usual understanding of time as a linear progression and suggests that the early universe might have been a playground for temporal anomalies. One of the most intriguing aspects of temporal displacement is its connection to the extreme conditions that existed right after the Big Bang. The universe was incredibly hot and dense, and the laws of physics as we know them today might have behaved differently. In this chaotic environment, spacetime itself could have been highly unstable, allowing for brief moments where objects or particles were displaced in time. Imagine a particle traveling through the early universe. Under normal circumstances, it would move forward in time along with everything else. But in the intense turbulence of the universe's infancy, it's possible that this particle encountered regions where spacetime was warped or twisted. In those regions, the particle could have experienced temporal displacement, causing it to jump backward or forward in time relative to its original trajectory. This theory gains further support when we consider the role of quantum mechanics in the early universe. Quantum fluctuations, which are random changes in energy at the smallest scales, might have created temporary pathways for temporal displacement. These fluctuations could have altered the fabric of spacetime, allowing particles to briefly escape the usual flow of time. Another factor to consider is the influence of gravity. In the dense early universe, gravitational forces were incredibly strong, and they could have interacted with spacetime in ways that enabled temporal displacement. For instance, a massive object or a black hole could have created a gravitational field so intense that it temporarily bent time, allowing nearby objects to experience a form of time travel. What's particularly fascinating about this theory is its implications for the development of the universe. If temporal displacement did occur, it could have played a role in shaping the distribution of matter and energy. Particles that experienced displacement might have ended up in regions of the universe they wouldn't have reached otherwise, influencing the formation of stars, galaxies, and other cosmic structures. As we ponder the possibility of temporal displacement in the early universe, it's worth asking how this theory connects to others we've explored. Could temporal displacement have interacted with primordial black holes, wormholes, or quantum entanglement? The more we uncover, the clearer it becomes that the universe's first moments were far more complex and mysterious than we once thought. Next, we'll turn our attention to the role of quantum fluctuations and how they might have created opportunities for time travel in the universe's earliest moments. Now, shifting our focus to the microscopic world, let's examine how quantum fluctuations could have paved the way for time travel in the universe's infancy. Quantum fluctuations are tiny, unpredictable changes in energy that occur at the smallest scales, and they're thought to have played a crucial role in the early universe. These fluctuations are not just random blips, they could have had profound effects on the fabric of spacetime itself. In the moments following the Big Bang, the universe was a seething cauldron of energy and particles, with quantum fluctuations constantly rippling through it. These fluctuations might have temporarily distorted spacetime, creating tiny bubbles where the usual rules of time didn't apply. Imagine spacetime as a smooth sheet of fabric, and quantum fluctuations as tiny ripples that momentarily crumple it. In those crumpled regions, particles could have experienced brief shifts in time, allowing them to move backward or forward relative to the universe's overall timeline. What makes this idea particularly fascinating is its connection to the uncertainty principle in quantum mechanics. According to this principle, certain properties of particles, like their position and momentum, cannot be precisely determined at the same time. This inherent uncertainty could have amplified the effects of quantum fluctuations, making it possible for particles to slip through time in ways that would otherwise be impossible. Another intriguing aspect is the scale of these fluctuations. In the early universe, the density of energy was incredibly high, meaning that even the tiniest quantum fluctuations could have had significant consequences. A small ripple in spacetime might have grown into a larger distortion, creating temporary pathways for time travel. These pathways could have allowed particles to jump across time, bypassing the usual constraints of cause and effect. This theory also ties into the concept of vacuum energy, the energy that exists in empty space. In the early universe, vacuum energy was extremely intense, and quantum fluctuations could have interacted with it to create temporal anomalies. These anomalies might have provided brief windows of opportunity for time travel, allowing particles to move through time in ways that defy our everyday understanding of physics. As we consider the role of quantum fluctuations in time travel, it's worth pondering how this theory fits into the broader picture of the universe's origins. Could these fluctuations have influenced the formation of cosmic structures like galaxies and black holes by altering the distribution of matter and energy across time? The more we explore, the more it seems that the universe's first moments were a complex interplay of chance and possibility, with quantum fluctuations at the heart of it all. Next, we'll delve into the final theory in our exploration, examining how the end of the universe might be connected to its beginning, creating a cyclical timeline that allows for time travel. Now, turning our gaze to the far future, let's explore a theory that ties the universe's end to its beginning, suggesting a cyclical timeline that could enable time travel. This idea hinges on the concept that the universe might not have a definitive end, but instead loops back to its starting point, creating an endless cycle of birth, death, and rebirth. Imagine the universe not as a straight line stretching from the Big Bang to a distant, cold demise, but as a circle where the conclusion of one cosmic era becomes the dawn of another. In this scenario, the end of time is not a finality but a return to the beginning. This cyclical model, often referred to as the Big Bounce, proposes that the universe collapses under its own gravity, only to rebound in a new Big Bang, starting the cycle anew. What does this mean for time travel? If the universe loops back on itself, the end of one cycle could be intricately connected to the beginning of the next. This connection might create pathways through spacetime, allowing for the possibility of time travel between cycles. For instance, a traveler at the end of one universe could theoretically jump into the next, bypassing the usual constraints of time as we understand it. This theory also raises fascinating questions about causality. In a cyclical universe, events at the end of one cycle could influence the beginning of the next, creating a web of cause and effect that spans across cosmic eras. This interplay could provide the conditions necessary for time travel, as the boundaries between past, present, and future blur within the loop. Another intriguing aspect is the role of dark energy in this process. Dark energy, responsible for the universe's accelerated expansion, might also dictate how the universe contracts and rebounds. If dark energy's influence changes over time, it could create the precise conditions needed for a big bounce, setting the stage for time travel between cycles. As we ponder this theory, it's worth considering its implications for our understanding of existence. Could the universe's first time traveler have come from its final moments, carrying knowledge from one cycle to the next? And if so, what might this mean for the nature of time itself? This brings us to the end of our exploration, but the journey doesn't stop here. Each of the 30 theories we've discussed offers a unique lens through which to view the universe's potential first time travel event. From the Big Bang to the Big Bounce, the possibilities are as vast and varied as the cosmos itself. So, which theory do you find the most compelling? Share your thoughts in the comments below, and don't forget to like, subscribe, and hit the notification bell for more deep dives into the mysteries of the universe. As we reach the end of our journey through these 30 extraordinary theories, it's clear that the question of the universe's first time travel is as complex as it is fascinating. From the Big Bang as a time loop to the potential of black holes as natural time machines, each theory offers a unique perspective on how time travel might have occurred at the dawn of existence. Some ideas, like cosmic inflation and temporal warps, focus on the physical conditions of the early universe, while others, such as the multiverse's first traveler, introduce the possibility of advanced civilizations crossing into our reality. Whether it's through quantum entanglement, dark matter, or the holographic principle, the diversity of these theories highlights just how much we still have to uncover about the nature of time and space. What's truly remarkable is how these ideas, while speculative, are grounded in cutting-edge science, pushing the boundaries of what we thought was possible. As we reflect on these theories, one question remains: which one do you find the most compelling? Do you believe the universe's first time traveler was a product of cosmic inflation, a visitor from another dimension, or something entirely beyond our current understanding? Share your thoughts in the comments below. We'd love to hear your perspective. If you enjoyed this deep dive into the mysteries of the universe, don't forget to like, subscribe, and hit the notification bell for more mind-expanding content. Until next time, keep exploring the cosmos and pondering the extraordinary possibilities it holds.